Let's do a real world application of differentiation. So differentiation gives us the slopes of the tangent lines to functions, or rather it's the instantaneous rates of change of functions. So if your function is position as a function of time, then what gives us the relationship between the change in your position and the change of time? Well, that's exactly what speed is, or velocity, right? How far do you move and how long does it take you to move that distance? So if I give you the position function as a function of time, you can differentiate this function with respect to time, and that is the velocity equation. So our position measured in meters as a function of time measured in seconds is given by P of t is 3 over t 2t plus 1. What is my initial velocity? So let's find our velocity function, and then we can evaluate it at time is equal to 0, at 2 seconds, and then at 20 seconds. So velocity is the first derivative with respect to time of position. That is the limit as h goes to 0 of the difference quotient p at t plus h minus p at t over h. P at t plus h is going to be 3 over 2 t plus h plus 1. P of t is 3 over 2 t plus 1. I divide all that by h. So we can't directly substitute just yet, or else the two terms in the numerator become each other, right? When h goes to 0, the left one becomes the right one. You get 0 over 0. So we need to do some algebraic manipulation here. And let's simplify a little bit in that first fraction. And so I can distribute the 2. You get 2t plus 2h plus 1. We won't change anything else. All right, now I have a subtraction of fractions in my numerator, and anytime I want to add or subtract fractions, I need a common denominator. The easiest way to do that is to give this denominator to this fraction, but you don't want to change anything, so you give it to the numerator and to the denominator. So we can rewrite that first fraction as 3 times 2t plus 1 over 2t plus 1, right? So those terms would cancel. I didn't change anything. The original denominator over there was 2t plus 2h plus 1. And we'll do the exact same thing. We'll give this fraction, this denominator, top and bottom. So minus 3 times 2t plus 2h plus 1 over 2t plus 1, the original denominator, and the 2t plus 2h plus 1. So again, we didn't really change anything. All of this is still sitting on top of an h. All right, but now notice, why did we do that? Because now our denominators are the same, right? Those two fractions in our numerator both have the same denominator. So I can just write that as one giant fraction. This is going to be 3 times 2t plus 1 minus 3 times 2t plus 2h plus 1 over that denominator, the common denominator. And then all of that is still sitting on top of an h. Okay, let's simplify that numerator a little bit. I'm going to distribute the 3. You're left with a 6t plus a 3 minus a 6t minus 6h. minus 3. Your denominator remains unchanged. And it's still sitting on top of that h there. All right, but that numerator, we see a lot of cancellation. 6t minus 6t plus 3 minus 3. You're really just left with a minus 6h over a 2t plus 1, 2t plus 2h plus 1. And then that is being divided by h. So here's an algebra trick. Anytime you have a fraction being divided by something else, which is what we have here, then instead of taking a divided by b in that quantity and dividing it by c, you can multiply it by its reciprocal, right? Taking a and dividing it by 4 is the same thing as taking a and multiplying it by 1/4. So effectively, you're really taking a and you're dividing it by b, and then you're dividing it by c again, right? So I'm taking a, dividing it by b, and divide by c. So I can really just bring this h into my denominator. Right, I'm just making, instead of a fraction sitting inside of another fraction, let's just make this one giant fraction. This gives you minus 6h over h times 2t plus 1, 2t plus 2h plus 1. And there's the cancellation that we needed. You're left with just a minus 6 over a 2t plus 1, a 2t plus 2h plus 1. And now that we've gotten rid of our problem, right, we performed that cancellation, let's try direct substitution now. If you send h to 0, your numerator is minus 6, and your denominator becomes 2t plus 1, and that factor also becomes 2t plus 1, right? That 2h goes to 0. So you've got 2t plus 1 squared down in your denominator. So let's just clean that up a little bit. Your velocity as a function of time is equal to minus 6 over 2t plus 1 squared. And now that you have your velocity function, you can evaluate it at any point that you want. All right, we should be good at evaluating functions now, so I won't go into a lot of detail, but if you take your velocity equation and if you look at it initially, so when time is equal to 0, your velocity equation returns a value of minus 6. So notice if your position was meters and time is measured in seconds, then the rate of change of that would be meters per second, right? That's a velocity. You're traveling 6 meters per second, and that negative just means that you're traveling backwards. So you're walking backwards at a rate of 6 meters per second initially. If you evaluate your velocity equation at 2 seconds, you get about minus 0.24 meters per second. So that negative still means that you're walking backwards, but now you're just not walking backwards quite as quickly. And if you evaluate your velocity at 20 seconds, you get minus 0.0036-ish, roughly. So you're still walking backwards, but you're walking backwards very slowly. Oh, forgot my units. Meters per second.